Good morning, students. In the previous lectures, we discussed about Fourier transform and its applications. And in today's class, we will discuss about Laplace transforms. So first of all, let us define Laplace transform for a function u belonging to the function space L1 R plus. Here R plus denotes the positive real line, means the open interval 0 to infinity. For such a function u, the Laplace transform is denoted by u hash. This is a function of variable s, which is given by integral 0 to infinity e raised to the power minus st u at t dt. Here this s is non-negative variable. So this expression is called the Laplace transform of the function u. Laplace transform is useful only for the functions which are defined on positive real line, whereas the Fourier transform is appropriate for all the functions which are defined on the whole real line or also on n-dimensional real Euclidean space. So, for a partial differential equation involving time, it may be useful to perform a Laplace transform in variable t, holding the space variable x fixed. Now let us discuss some examples related to Laplace transforms. Our first example is resolvents and Laplace transform. Let us consider the heat equation given by partial derivative of v with respect to t minus Laplacian of v is equal to 0 in u cross open interval 0 to infinity, and when time is 0, then value of function v is f. Now, by definition, if we take the Laplace transform of function v with respect to time, then it is given by v hash is equal to integral 0 to infinity e raised to the power minus st v at xt dt. Here s is positive variable. Now, v hash satisfy which partial differential equation? To discover this, let us find the Laplacian v Laplace transform. By definition, Laplace transform of Laplacian of v, that is given by integral 0 to infinity e raised to the power minus st into Laplacian of v at xt dt. Now, because we are given that function v satisfies the heat equation vt minus Laplacian of v is equal to 0. So from here we can see that Laplacian of v is given by vt. Vt means partial derivative of v with respect to t. This t is in the base of v. Substituting the value of Laplacian of v here. So, the Laplace transform of Laplacian of v at xs is given by integral 0 to infinity e raised to the power minus st into partial derivative of v with respect to t dt. Now, let us solve this integral by using integration by parts. Taking this function as first function and vt as second function. First function as it is, integration of function vt, that will be v between the limits 0 to infinity minus integral derivative of this function, that will become e raised to the power minus st into s. Integration of this function which is V. Now substituting the limits here, if we put infinity, this will become 0, and add 0, e raised to the power 0 will be 1. So we get V at the point x0 plus s integral 0 to infinity e raised to the power minus st V at xt dt. Now we are given that when time is 0, value of function V is f. So this will become f at x. So the Laplace transform of Laplacian of V at x is, that is given by minus of fx plus s integral 0 to infinity e raised to the power minus st V at xt dt. Now by definition, this expression is the Laplace transform of function V. So from here we can say that the Laplace transform of Laplacian of V with negative sign plus s into Laplace transform of V is equal to f. If we take the Laplace transform of function V defined to be as u, then from this equation we get negative of Laplacian of u plus su is equal to f in u. So from this equation we can say that the function which is Laplace transform of V, that is the solution of this equation. This equation is called the resolvent equation, and its solution, which is Laplace transform of V, that is obtained by taking the Laplace transform of the solution of given heat equation. So this was one of the examples for the Laplace transforms.